Hi, today I will be working on a balloon age prediction dataset, and this is a regression problem. The goal of this project is to predict the age of a balloon using its physical measurements. In this dataset, the target variable is rings, which represent the number of rings on the balloon shell. Since a balloon age is commonly estimated by counting shell rings, the age in years can be approximated as age equals rings plus 1.5. For the data overview, the dataset contains 4177 observations and 8 input features. The features include one categorical variable, a sex, and 7 continuous variables, length, diameters, height, hull weight, shaft weight, visceral weight, and shear weight. Because the target is numerical and continuous, this is clearly a regression task. So classification model like logistic regression are not applicable. Before modeling, I first performed a basic data quality check. The dataset contains 0 missing values and 0 duplicate rows, so no imputation or duplication was needed. Next, I confirmed that sex is the only categorical feature with 3 category F and I, while the remaining features are continuous numerical measurements. Since machine learning model require numerical inputs, I encoded sex using label encoder. To better understand the dataset, I combined X and Y into one data frame and used AutoVis to generate some summary statistic and visualizations. From the Schooner's analysis, most features were moderately good, but height stood out with a Schooner's around 3.13, indicating strong right Schooners and possible extreme values. I also checked the target distribution and ring size as Schooners around 1.11, meaning the target is also right good. Since extreme target values can strongly influence regression performance, I performed outlier detection of rings using the Turkey IQ rules, remove those outliers from both X and Y, and confirm the effect using a box plot. Finally, I reviewed relationships among features using scatter plot and a correlation heat map. The heat map showed that many physical measurements are highly correlated, especially length, diameter, height, and weight-related variables. This indicates from multicollinearity, which can affect linear models, while tree-based models are generally more robust to correlated predictors. After pre-processing, I moved to modeling preparation. I split the data set into training and testing sets using an 80% training and 20% testing split results in there are like 3341 training samples and 836 testing samples. Importantly, the split was done before scaling to avoid data leakage. Then applied feature scaling in the notebook. Both standard scaler and Minimax scalar are shown. Scaling is especially important for models sensitive to feature magnitude, such as KNN, SBR, and neural networks, and it can also improve stability for linear models. For the future importance, before comparing multiple models, I trained a random forest regressor to compute feature importance. From the feature importance plot, shear weight was by far the most important predictor, contributing around 0.5 of the total importance. The next most important features were shaft weight, followed by other weight-related variables. This result in intuitive because shear and body weight are strong indicators of the balloon's growth stage, which is directly related to age. After pre-processing, I trained and compared multiple regression models on the same 80-20 train test split, including multiple linear regression, ridge regression, lasso regression, elastic net, KNN, SVR, decision tree, and multi-layer perceptual. I selected these models because they represent different levels of complexity and different assumptions. Linear model provided a strong and interpretable baseline, KNN and SBR, can capture nonlinear relationships, which are often present in biological growth patterns. Decision trees model nonlinear reality directly but may overfit, and MLP can learn complex patterns if the relationship is higher nonlinear. Overall, the best performing models were multiple linear regression and range regression. Both models achieve an R square equal of about 0.53 with an MSE around 5.1 and MAE around 1.61. They suggest that the relationship between the abalone's physical measurements and its age is largely linear, or at least well captured by a linear baseline model. Ridge regression performed almost identically to standard linear regression. This is meaningful because the correlation heat map showed strong multicollinearity among predictors. Bridge regularization helps stabilize confusion under multicollinearity, but in this dataset, it did not significantly improve predictive accuracy. In comparison, the MLP narrow network and KNN regression also performed reasonably well with R square values around 0.5 to 0.51 and MAE close to 1.6 rings. This indicates that there may be some nonlinear patterns, but the improvement over the linear regression was limited. On the other hand, several models perform much worse. For example, lasso regression had an R square equals 0.14 and 8, and its coefficients were almost all reduced to 0. Oh, they suggest that the model select too few predictors and underfit the data. The decision tree model also performed poorly with a R square of about 0.21, which suggests overfitting and weak generalization on test stat. Finally, from a practical perception, the best models achieve a mean absolutely error of about 1.6 rings since a balance age is a pro-max state but age equals rings plus 1.5. This corresponds to an average prediction error of roughly 1.6 years, which is reasonable interpretable for real-world use. These findings have several important ramifications for the actual world. First, the fact that ridge regression and linear regression perform the best indicates that there is a consistent and predictable relationship between a balloon age and physical size and weight. This implies that without the need of extremely complicated algorithm, straightforward and comprehensible models can already produce reliable forecast. Second, shear and body weight variables, particularly the shear weight, contribute more to the prediction of rings according to feature important analysis. Given that older balance often grow heavier shear over time, this make biological sense. Practically speaking, age estimate is sustainable harvesting and population planning in real-world context, like fishes management, aquaculture operations, and in ecological monitoring, while an average inaccuracy of roughly 1.6 years may be helpful. However, there are restrictions. The predictors exceed high multicollinearity, while the target variable rings is rise good and contains outliers. Performance and stability may be lowered by this issue, particularly for models such as decision tree. All things considered, this research emphasized how crucial it is to combine meticulous pre-processing, correlation analysis and model comparison. A well-organized workflow can generate significant and comprehensible predictions even with a comparatively small dataset.